Hello everyone, welcome to this lecture on rank of a matrix, which is a very important concept in linear algebra. I am Dr. Vikrant Yadav, Assistant Professor in Department of Mathematics at SR University, Parangal. In previous lectures, we studied topics like row echelon form and reduced row echelon form, which help us simplify matrices using row operations. Today, we will build on that knowledge and understand how those forms help us determine the rank of a matrix. The concept of rank is extremely important because it helps us understand how many independent rows or columns a matrix has, whether a matrix contains redundant information, whether a system of equations has unique solutions, infinitely many solutions, or no solution, whether a matrix is invertible or singular. In many applications like data science, engineering, and machine learning, rank tells us whether information in data is independent or redundant. So, in my view, understanding rank is not only mathematically important but is also practically useful. So, let us start by first looking at the outline of today's lecture. Let us briefly see what topics we are going to cover today. The lecture is divided into two parts. Part 1 is theoretical one and part 2 is solved examples. In part 1, we'll be basically covering up the definition of rank, how to compute rank with row reduction, then the concepts of row rank and column rank, then some important properties of rank, and after that, the rank nullity theorem. Okay, in part 2, we will see and apply these concepts to several examples. First example is like finding the rank of 3 cross 4 matrix. Second will be of the order, matrix will be of the order 4 cross 4. And we'll find out the rank of that matrix. Then determining whether a matrix is invertible or not using rank method. Then applying rank nullity theorem to find the rank of a matrix. Then determining rank when a parameter is present in a given matrix. Okay, and at last we'll be summarizing the key formulae and concepts. Okay, let us begin with the definition of rank. The rank of a matrix A, written as rank of A this way, is defined in several equivalent ways. Okay, the first one is the rank of a matrix is the number of pivot columns or in its row echelon form or reduced row echelon form. When we reduce a matrix using row operations, some columns contain leading entries. Okay, those entries are known as pivot entries. Okay, so the number of these pivot positions gives the rank. This is first way of defining rank. Secondly, the rank of a matrix is also defined as the dimension of column space. This means it counts how many columns as are linearly independent. Okay. Similarly, rank can also be defined as the dimension of row space, which means the number of linearly independent rows. Okay. And a very important theorem states that row rank will be definitely equal to column rank, and therefore we simply call this number as the rank of the matrix. Okay, means both column rank and row rank will always be equal. Then some intuitive meaning of rank is also there, according to which we can say think of rank as measuring amount of independent information in the matrix. Okay, What do you call it? Independent information in the matrix A. If some rows are multiples of others, then those rows do not add new information. That's it. And therefore, they do not increase the rank. Okay. So basically, we count for the number of independent rows and which will give the rank. To understand it, let us see some quick examples. Consider the matrix, this one, rank 1001, in which both the rows are independent. Okay, rows as well as columns are independent. So the rank is basically 2 here. But in second matrix 1, 2, 2, 4, both the rows in the first row, if you multiply first row by 2, then it will become the equal to second row. So it is not independent. Okay, so one row is dependent upon the other. Therefore, the rank is basically 1. Similarly, in the third example, all elements are 0. So its rank is 0. Basically, it is a 0 matrix. Okay, so its rank is 0. Now, let us see how we compute rank of a matrix. Okay, the most common method is called row reduction. We reduce the matrix to row echelon form using elementary row operations. Okay, step 1 involves writing the matrix A. Then in step 2 we apply elementary row operations. Okay, until the matrix becomes in its row echelon form. These operations include row swapping, that is interchanging two rows. Row scaling means multiplying a row by a non-zero scalar, and then row replacement, that is a row is replaced by with its sum with some other with the scalar multiple of some other row. Okay, let me write them here. First one is Ri interchange with Rj. Second one is Ri change to k times Ri. And third one is Ri change to Ri plus k times Rj. Okay, these are three elementary row operations that we use to just convert any given matrix into row echelon form. In step 3, we count the number of pivot rows or non-zero rows. Okay, that number is basically the rank of matrix. Now, there are some important facts that we must be aware of. There are several points like first one, the rank of the matrix A will be greater than or equal to 0, but it will be less than or equal to the minimum of m comma n. M comma n is here. M is the number of rows, n is the number of columns. The least m or n, okay, minimum of them. Suppose a matrix is there which is of the order 2 cross 3. In this case, rank will be less than or equal to the least one, that is 2. So rank will be less than or equal to 2, not 3. Okay. Then second point is rank of A and rank of A transpose are always the same. Then third one, elementary row operations do not change the rank. And this is the most important point in here. Elementary operations do not change the rank of a matrix. Okay. Now there is one more definition, like what do you mean by full rank? If the rank of a given matrix equals the maximum possible value, then that matrix is called full rank. Okay. That matrix is called full rank. For square matrices, full rank means matrix is invertible. If any matrix which is square matrix it is having full rank, it will mean that the matrix will be invertible. I hope you are getting the point, and it is really, really important. Okay. Now we come to one of the most important theorems in linear algebra, the rank nullity theorem. For any matrix A with n columns, the rank plus nullity equals to the number of columns. Okay, and this theorem is known as rank nullity theorem. Now you will ask, what is nullity? Nullity represents the dimension of the null space. This nullity represents the dimension of the null space. Okay, it also equals to the number of free variables in the system. That is a very important point. It is basically equal to the number of free variables in the system. Now, suppose a matrix is having 5 columns. If the matrix say M cross n order is having the value of n as 5, and the rank of A is equal to 2, then its nullity must be 5 minus 2 equal to 3. Okay, this means that there are three free variables in this system. Okay, now some important consequences of nullity theorem, rank nullity theorem we'll be looking at. If rank is equal to n, then nullity must be 0 only. So for rank of a less than n, this equation I'm talking about, rank of a less than n, there are definitely free variables, which means the system has infinitely many solutions. Which system? System is Ax equal to 0. Okay. If the rank of A is less than n, that means nullity is definitely greater than 0, and which means the number of free variables are there. Some free variables are definitely there, which means there are infinitely many solutions for the system Ax equal to 0. Okay, so and one memory aid also is there. You can remember it, that rank is dependent info, nullity is for free. What is free in it? Okay, that should be equal to the total number of columns. Am I clear to all? I think it should be clear. Okay, so now let us apply these ideas to an example. We are given an example, our matrix of the order 3 cross 4. Okay, order of this matrix is 3 cross 4. Our goal is to find its rank. First, we apply row operations to convert the matrix into row echelon form. After that, we'll find out its rank. Okay. So in the first step, we are going to choose the first non-zero entry in the first row, that is equal to 1, this entry. With the help of this entry, we are going to make 0 here and here. Below it means. Below this, we'll be making 0. Okay. So for that, I apply the operation R2 change to R2 minus 2R1, and for third row I am applying R3 change to R3 plus R1. So this gives me the following matrix. Okay, now I see in this matrix that everything is 0 below this one, the first pivot entry. Okay, after that I need to make 0 below the next pivot entry in the next row, but here the next pivot entry is at this place, that is equal to 1. Okay, so I need to make 0 below this one. So with the help of this one, I'll be making 0. This part in 2 will have to become 0 only. Okay, so in the next step, I applied the operation R3 change to R3 minus 2R2. Okay, so after that I'm getting this kind of matrix as you can see on the screen. Now again next row and next pivot entry. So next one is 2. Okay, and this pivot entry 2, there is below this pivot entry 2 there is nothing there, means no more rows are there. So let it be like that only. Okay, so now we see that there are three pivot, or definitely we can make this value equal to 1. If we leave that as it is, then also it is not a problem because we are converting that into row echelon form only. So this is pivot entry, this is pivot entry, and this last one is also pivot entry. So number of pivot rows are 3. Okay, so nullity will be equal to, now you'll be thinking like what about this 2? This is a column. Okay, this column will be for free variable. Okay, so rank equals to 3 and nullity will be equal to, according to rank nullity theorem, what can you say? Rank of A plus nullity of A will be equal to the number of columns, that is 4 here. So nullity is going to become 1, and that is the result from this for this matrix. Okay, am I clear? Okay, now let us see one more example of a 4 cross 4 matrix. Okay, here the order is 4 cross 4. That means 4 rows are there and 4 columns are there. So let us start changing it into row echelon form so that we can find out the first pivot entries and then the rank of the matrix. Okay, so for this matrix, the first non-zero entry, the pivot entry is 1 here. Okay, with the help of this one, I need to make all the three entries below this equal to 0. So I have applied these operations, say row 2 change to row 2 minus 2 times R1, row 1, and then second operation I applied for third row is row 3 change to R3 minus row 1, R3 plus row 1. Okay, so I got this kind of matrix. So our first pivot entry is this one, which is represented in red one. Then next row is basically having the first non-zero entry, this red again. So with the help of this one, we are going to make 0 below it. Okay. So after this, we'll get some kind of matrix. Let us see what we get. So I applied the row operations like R3 changed to R3 minus R2. Then for row 4, I applied the operation R4 changed to R4 minus 2 times R2. Okay. So I got this kind of matrix, and this is a very special form in which we have gotten like third row is completely 0 and fourth row is completely 0. Okay. Are you able to see? The third row and fourth row both are completely 0. Okay, so we are getting two pivots here. This one A11 place and then this is A22 place. Correct? That means the rank of this matrix is basically rank of this matrix A is 2. But here the number of columns n is 4. So definitely that is going to make, according to rank nullity theorem, 2 plus nullity of A equal to 4. This is the rank, this is nullity. So what is the value of nullity? Nullity will be Na equals to 2 again. Okay, that means there are two non-zero, there are two variables which are free. Okay, two pivots are there. After that, one more, we can infer one more information from here. That is, since the number of free variables is 2, nullity is no 0, so B is not invertible or you can say since it is a square matrix which is not invertible, we can call it as singular matrix. Okay, that is also known as singular matrix. So now let us see one more example of a singular matrix. Okay, last example was also singular, but it is particularly for this purpose only. Let us say this matrix C, which is having 3 rows and 3 columns, that is of the order 3 cross 3. Now, first choose the first non-zero entry in the first row, that we will make it as pivot entry. With the help of this one, make 0 below it. Okay. For doing that, I applied these two operations. Those are row 2 change to row 2 minus 2 times row 1, row 3 change to row 3 plus 3 times R1. So what happened actually? I got this kind of matrix which is having first row, only the first row has 0 row. Okay, not the no 0 row, and other two rows become 0. So we are having one non-zero row and other two rows are 0. Okay, so this first entry can be made as pivot entry, other two are two rows are 0. Okay, what after that? From here we can conclude that since only one pivot entry is there, so we can have rank of C equal to 1 and nullity of C as 3 minus 1, since the number of columns is 3 here. Okay, so it is equal to 2. Okay, so since it is a square matrix, so we can calculate the inverse as well. So from here we can see that since only one pivot entry is there, rank is 1, so we cannot calculate the inverse. It is non-invertible, not invertible basically, and it is a singular matrix. Okay, determinant will be 0, nullity is 2, and so all rows are, not all, two rows are linearly dependent. Okay, in particular if you see all rows, so all will be dependent only. Okay, so now let us see one more example which we will be solving using rank nullity theorem. So in this example we are required to find the rank, nullity, and describe the solution sets. Okay, in the first step I chose this value 1, okay, which is the first pivot entry or the first non-zero entry in the first row. With the help of this one I made 0 here, which is already 0, here also 0, and here also 0. We need to do it. Now for that I applied the operations like row 3 change to row 3 minus 2 times R1, row 4 change to row 4 plus row 1. Okay, so I got this kind of matrix basically here. Then everything below this one first non pivot entry is 0. Okay, next column will definitely be free for the free variable. Okay, then next pivot entry is this one, which is at the place second row third column. Now with the help of this one I need to make 0 here and here. So I applied the operations row 3 change to row 3 minus row 2, and again row 4 change to row 4 plus row 2. So I got this kind of matrix which is having the row number 3 and row number 4 as completely 0. So from this I can say the rank of this matrix T is 2. Okay, so nullity will definitely be number of columns, that is equal to 5 minus rank of A, rank of this matrix D, that is equal to 3. Okay, now the pivot columns are basically first column and third column. Apart from that, there are three free variables which are lying in the column like column 2, column 4, and column 5. The solution of this system dx equal to 0, basically it will be having infinitely many solutions because rank of D is 3. The nullity of D is non-zero. That is equal to 3 here. Okay. There are three parameters or variables which will make it have these solutions, infinitely many solutions. So this system is consistent. It is having solutions. Solution of dx equal to b, that is non-homogeneous system of linear equations, it will have the solution if it is consistent. Okay, that's it. I hope you're getting it. Okay, now let us see one example where the rank is depending upon a parameter in the matrix. Okay, so basically see this example where in this matrix C we are having a parameter k, and the value of rank will depend upon this parameter k. Let us see how. So for solving this, methods will be same, procedure will be same. First we need to choose the first non-zero entry in the first row, which will be the first pivot entry. Okay, that is equal to 1. With the help of this one, we are required to form one here and here. Let us do it first. Okay, so I applied the operation row 2 change to 2 times row 2 minus 2 times row 1, and row 3 change to row 3 minus row 1. Okay, so I got this kind of matrix. Okay, now everything below this first pivot entry in the first row is 0. I choose the second pivot entry in the second non-zero entry in the second row, that is equal to 1 again. Now I need to make 0 below this. So I am getting this kind of matrix by applying the operation row 3 change to row 3 minus row 2. Okay. So I got this kind of matrix basically, in which I am having this entry as k minus 6 and the last A33 entry at the third row and third column place 9 minus k. Now the following cases arise from this. If suppose your 9 minus k in the third row is non-zero, that means if k is not equal to 9, in that case it will become the pivot entry and this matrix will be having rank equal to 3. In that case, this matrix E will be invertible because rank is equal to the maximum, okay, maximum possible value. So it is invertible. Okay. Now, if the value of this k is 9 minus k equal to 0, in that case k equals to 9 and the rank becomes 2. Okay, so this matrix A will become singular, it will not be invertible, and determinant will be 0. Okay, so the question was for what value of k does rank is less than or equal to less than 3, basically this was the question. So our answer is for rank will be less than 3 if k equals to 9. Okay, and that is the answer here. So there are the properties of rank. The fundamental properties involve rank of a given matrix A will be greater than equal to 0 and less than equal to rank minimum of the number of rows and columns. Okay. Second property involves rank of A and A transpose are equal. Then rank of product of two matrices is less than equal to minimum of rank of A or rank of B. Okay. Then rank of A plus B, that is sum of two matrices, is less than equal to rank of A plus rank of B. Again, multiplying a matrix by a non-zero scalar does not change the rank of the matrix A. Also, for a square matrix of order n, we have rank of A equal to its order. Okay, then A will be invertible. If the determinant is non-zero, then Ax equal to B has unique solution. Okay. Also, we are having these properties like rank for any system, given system, augmented matrix A augmented B or Ax equal to B system. Let me write the system here, Ax equal to B. Okay. For this system, we are having if rank of A is less than rank of A augmented B, then it will be inconsistent. That is, no solution will be there. If the rank is of A is equal to rank of A augmented B equal to the number of columns, unknowns basically, unknowns, then it will have unique solution. If the rank of A and rank of A augmented B, okay, are equal but less than the number of unknowns, then this system will have infinitely many solutions. Okay, and finally there is rank nullity theorem, which states that rank of A plus rank of A nullity of A will be equal to the number of columns. Okay. Thank you for watching this lecture on rank of a matrix. I hope this explanation helped you understand the concept clearly. If you found this lecture useful, please like the video, share it with your classmates, and subscribe for more lectures on linear algebra and mathematics. Thank you.